Hello, in this session we'll discuss about D block elements, the general properties of D block elements, special properties of D block elements. It's little lengthy topic, so we'll discuss it in 1-2 classes. Okay now. So consider this is part class or is a part 1. D block elements. D block elements means the newly coming electron or the differentiating electron which is coming at the last, it is going to enter into d orbital. Generally you can say n minus 1 d orbital. So that is entering into the d orbital, then they are called as d block elements. Differentiating electron enters into the d orbital, so called d block elements. See, scandium 3d1, titanium 3d2, first 3d elements. Okay, so d block elements, you can call them transition elements also, except this zinc, cadmium, mercury, copper, nickel, except that group you can say the remaining all elements as transition elements. The reason for the transition elements is, the definition is, outermost two shells are incomplete. When outermost two shells are incomplete, you can call them as transition elements. In their ground state electronic configuration are most stable oxidation states. Okay, now for example, you see copper. Copper is 4s1 3d10. You can say D10 configuration is there now, but copper stable configuration is in the stable oxidation state configuration is copper plus 2 3d9. So there it will be in turns in transition series. Okay, so these are the elements: scandium, yttrium, lanthanum, actinium. Okay, this is third B, fourth B, fifth B, sixth B, seventh B. Iron, cobalt, nickel, all these elements are 8th group according to Mendeleev table. This is first B and this is second B. IUPAC system 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 group numbers. The general electronic configuration is NS1 to 2, N minus 1D 1 to 10. For D block transition elements, both the same. NS1 to 2, N minus 1D 1 to 10. But chromium special, chromium is 3d5 4s1, molybdenum 4d5 5s1, tungsten 5d5 6s1, these three, because they are getting half well stability because of that exceptional electronic configuration. You can see here copper, silver, gold, 3d10 4s1, 4d10 5s1, 5d10 6s1, fulfilled. Surprisingly, you can say interestingly, there are few elements like niobium. We expect like vanadium 3d3 means it should be 4d3, but surprisingly it is 4d4 5s1. Then iron 3d6, so we are expecting ruthenium also 4d6, but ruthenium is 4d7 5s1. Rhodium 4d8 5s1. Palladium is little bit more advanced. This is having 4d10 5s0. When it is having 4d10 5s0, don't expect the same with platinum. Platinum it is having 5d9 6s1. 5d9 6s1. This you can explain. This may be because of electronic repulsions and electron nucleus attractions. We can say maybe possible because of that. Here lanthanum, actinium, after lanthanum there are 14 lanthanum elements, after actinium there are 14 actinoid elements, cerium to lutetium, thorium to lawrencium, they are present here. And you see, these are HCP structures, crystal structures, metal crystal structures, you can say HCP, hexagonal close packing, BCC, HCP again, CCP, and again HCP. Okay, now there is no technique to remember. You can't apply any logic by seeing this or tantalum or tungsten will be BCC. You cannot. Just try to remember, or you make any shortcut like that. Iron BCC and cobalt is HCP. They are exceptions. They are not like this. That point you can notice. So we were discussing about the electronic configuration and series. 3D series, 4D series, 5D series, and 6D series. Each series there are 10 elements. 3D series means the electrons are entering into the 3D orbital. They are 4D, 5D and 6D. Few properties we need to discuss. In that, the first one is atomic radius. Down the group, atomic radius should increase. True. In case of scandium, yttrium, lanthanum, actinium. That's true, definitely. But in the remaining cases, 3D to 4D radius increases. Correct. But 4D to 5D, the radius is almost same. As you say, whatever the increase is there, the increase is very, very small. Okay. And here, instead of increasing, it will be small decrease. Or in general, you want to say 3D to 4D radius increases, 4D to 5D, 5D to 6D, the radius is going to be almost same. The reasons are because of lanthanides, because of actinides. Lanthanides cause lanthanide contraction. In actinides, due to the poor screening of F5 F orbital, there will be actinide contraction. Because of lanthanide contraction, because of actinide contraction, that effect is still there up to here. 3D to 4D radius increases. 4D to 5D, 5D to 6D radius is almost same. Or you can say here slight increase, here slight decrease is there. Okay, that's about atomic radius. Here is an order you can see. Scandium, titanium, actually across the period it should decrease, but zinc is here, exception. Okay, vanadium, copper is here, again exception. Remaining are in regular order. Okay, scandium, titanium, zinc is coming before vanadium, copper is coming before chromium, remaining elements are as it is. So I just mentioned here 3D to 4D, 4D to 5D, 5D to 6D, how the atomic radius will change. These properties will take, we will discuss after taking some atomic volumes, atomic densities and volumes. Okay, atomic volumes are less, atomic density are more, because density is directly proportional to what you can say mass and inversely proportional to volume. Okay, density is called mass by volume. As I said, volumes are less, and as the masses are going to be increasing across the period down the group, so densities are going to be more. Osmium is the densest element you can say. These are the regular things. Then ionization potential, one again very interesting property. Scandium to yttrium, okay, scandium to yttrium, if you see the ionization potential, yttrium to lanthanum, lanthanum to actinium, here in this slide, that is absolutely atomic radius increases, so IP decreases, regular trend, done. But here you see 3D to 4D, atomic radius increases, so IP decreases, correct. 4D to 5D, atomic radius is almost same, or what is it? A slight increase is there. So ionization potential, slight decrease will be there. Okay. Otherwise you can say almost the same. Otherwise you can say they are very close. You cannot atom to atom you cannot say. Okay. Now, in general only we are saying. So what I said 4D to 5D, 5D to 6D. Your atomic radius slight increase is there. So ionization potential slight decrease. Your atomic radius slight decrease is there. So ionization potential slight increase will be there. Okay. So no question of asking particularly iridium to medium what happens. Such kind of questions they won't ask you. That's about ionization potentials. Okay. Then alloys. These elements are ready to form alloys. To form alloys, the major quality should be atomic radius must be similar. So they are almost having similar sizes. So comfortably they can join with each other and they can form alloys. Okay. Copper and gold, we know that forms a very good combination, copper and gold. Okay, now gold, pure gold is what we say in market, 24 karat gold is pure gold. Yeah, if you are having 22 karat gold, that means ornamental gold is 22 karat gold. It is not pure 24 karat gold. What we call biscuit gold. Okay, now that is pure gold. 22 karat gold means that is either mixed with cadmium or mixed with copper, in order to increase the malleable and ductile conditions, so that that can be converted into ornaments easily. 18 karat gold means that is 75% pure. So like that you can say. So these are ready to form the alloys. Okay. 2-3 examples if you want. Bronze, brass you can take. Bronze is a combination of copper and tin. Brass is a combination of copper and zinc. Okay. Like that you can take alnico. Alnico is aluminium, nickel and cobalt. Other examples you can take stainless steel, or not related to D block elements, but alloys means you can remember these examples. Magnesium, aluminium bronze. Aluminium bronze is aluminium and copper combination. Magnesium is magnesium and aluminium combination. So these you can take. They are ready to form the alloys. Next one, interstitial compounds. What do you mean by interstitial compounds? Interstitial means you take some metal into the liquid form and allow it to become a solid. When it is becoming a solid, you pump a gas into that one, or you add some small groups like boron, carbon, nitrogen, oxygen, small second period elements, you can say. You just send them into that one. Into the metal crystal gaps, these small elements can be trapped, can be arrested, you can say, inside. Such kind of compounds are called interstitial compounds. Interstitial compounds won't have proper stoichiometry. Interstitial compounds are going to be less stable. If you are going to heat them, they simply come out. Okay, now those compounds are going to be coming out. Interstitial compounds, I am saying. Okay, now. And interstitial compounds examples you can take. If you are taking hydrogen, they are called hydrates, carbon carbides, nitrogen nitrites, oxygen oxides. All these are the elements. Boron, borides, you can say interstitial compounds. Interstitial compounds, you can say they are crystal defects. Okay, now the crystal is not, for example, you are taking silver. That is not with all silver atoms. There are some gaps. Okay, now some questions you can say W 0.98H. WH formula, tungsten hydrate. We are writing W 0.98H means there is no proper stoichiometry. Such kind of compounds you can call them as interstitial compounds type. Okay, non-stoichiometric compounds these are, because there is no proper chemical bonding. They are just trapped inside them. Because of that, the rigidity increases, the hardness increases. These are some properties of the interstitial compounds. Interstitial compounds. Then we need to discuss the oxidation states. Before going to oxidation states, we'll have a look at this. As you can see, oxidation state increases, the covalent character is increasing. Vanadium +2, +3, +4, +5. Covalent character is increasing. Oxides, you see, lower oxidation state oxides are basic. Intermediate states you can say amphoteric, and higher states are acidic. This is best example. Chromium oxide, basic. Cr2O3, CrO2, amphoteric. CrO3 is going to be acidic. MnO, Mn2O3, basic. MnO2, Mn2O5, +4, +5 states, amphoteric. MnO3, acidic. Mn2O7, strongly acidic. But no rule, don't think that this is a rule forever. Iron oxides are only basic. Iron oxides are only basic. Then you see, H2CrO4 is chromic acid. So chromic acid salt it is, you can say chromic acid anion it is. And such anions, when they are there, okay, down the group the anion stability increases. You can see CrO4 -2, MoO4 -2, and WO4 -2. Down the group the stability increasing. When the stability increases, oxidizing nature decreases. CrO4 -2 is strongly oxidizing. You can see the same in 7th B group also. Manganese, technetium, rhenium. Okay, now this is from HMnO4, permanganic acid. From that you are getting this anion part. This anion is more oxidizing in nature, and this is going to be more stable in nature. So I would like to give you the oxidation states. For that purpose, I will go up to here. One simple line I will mention here. You remember that line. That is, the minimum oxidation state is equals to number of s electrons. Maximum oxidation state is equals to number of s electrons plus number of unpaired electrons in n-1 d shell. Number of s electrons is minimum oxidation state. Number of unpaired electrons in n-1 d shell plus number of s electrons is the highest oxidation state, you can say. The electronic configurations are like this: 4s2 3d1, 4s2 3d2, 4s1 3d5, these are the electronic configurations. Now, The minimum oxidation state means number of s electrons. So it should be 2. But surprisingly, interestingly, there is no +2 state for scandium. Scandium shows only +3 states. +2 and this one. So for scandium, only +3 is the oxidation state. Titanium. Titanium oxidation state. The minimum oxidation state is number of s electrons +2. The number of unpaired electrons in the d orbital, you can see here. These are the d subshell. 5 orbitals, 2 unpaired electrons are there. So add both of them. Vanadium, 3 unpaired electrons are there, minimum +2. Then add 3 more. The highest is +5. Chromium, 4s1 configuration is there, so minimum is +1. 3d5, 5 unpaired electrons are there. So add +5, +1 to +6 possible. The minimum is +2 here. Add 5 more. +4, +5, +6, +7. 4s2, +2. And iron, +4 is also rarely showing. +2, +3 is only for iron generally. Cobalt, actually cobalt 3d7 means up to here. So these 3 should be added. +2, +3, +4, +5. Well, cobalt +5 state actually we can show, but very rarely possible. These also you can show based on the number of electrons you can show, but these are not there. So generally up to here only it will show. Nickel +2, +3, +4. And copper is +1. It should show only +1 because D is completely filled, but +2 is very special for copper. Scandium, we are expecting this, not possible. Copper, we are not expecting this, but it is possible. Okay, now zinc, it is +2. So these are the oxidation states. You can see oxidation state gradually increasing, then gradually decreasing. Okay, now up to 7 it is increasing, then it is decreasing up to 2. Okay. Remember scandium +3. Except scandium, for all D block elements you can say the common oxidation state is going to be +2. D block elements common oxidation state is +2. Not relevant here, but you can remember for F block elements it is +3. Common oxidation state is +3. In 3D series, the highest oxidation state is for manganese. 3D series, the highest is for manganese. In the remaining series overall, if you see osmium and ruthenium, they are with +8 oxidation states. The highest possible oxidation states +8, osmium, ruthenium, even you can take xenon tetroxide, XeO4, OSO4, ReO4. Okay, now +8 is possible, that is the highest oxidation state. 3D series maximum is +7. For F block common +3, for D block common oxidation state is +2. This is about the individual oxidation states of 3D series elements. Scandium, you remember that should be +3 only. Titanium generally shows +4. Vanadium can show up to +5. Chromium shows +6 comfortably. +3 also it shows. Manganese +2, +7 generally it is showing. Iron +2, +3. Ferrous, ferric we know. Cobalt +3 generally it shows. Nickel +2. Copper +1, +2 both are there, but +2 is only more stable. Zinc is +2. This is about the oxidation states of these elements. Okay. In next part, we will discuss about magnetic nature, color property. Magnetic nature, color property, and little bit introduction to the coordination chemistry. Done?